Hello there everybody. In this video course on fluid mechanics, the main objectives are introduce fluid mechanics and establish its relevance in civil engineering, develop the fundamental principles, demonstrate how these are used in engineering, especially in civil engineering field. This video course consists about 40 lectures presenting the concepts, theory and applications. The important topics covered in this course include the fundamental concepts of fluid flow, fluid statics, kinematics of fluid flow, dynamics of fluid flow, laminar and turbulent flows, pipe flow systems, dimensional analysis, Navier-Stokes equations and applications, and boundary layer theory and applications. So, in these 40 lectures, all these topics will be covered with various examples, with the theories and fundamental principles. The important references used in this course include the fundamentals of fluid mechanics by Bruce Amundsen and others, the fluid mechanics with the engineering applications Dougherty and others, fluid mechanics by Douglas and others, fluid mechanics by Granger, fluid mechanics by Streeter and Wiley, and mechanics of fluid by Shames. Okay, in this introductory lecture today, we will discuss mainly the fundamental concepts and fundamental properties and fundamental definitions of fluid mechanics. So, the main objectives in this lecture are to discuss the nature of fluids, to introduce fluid properties, discuss the flow characteristics, discuss the flow visualization techniques and illustrate the foundations of fluid flow analysis. So, all of you know the importance of fluid mechanics. It is the most important subject in all science, including physics, chemistry, biology and mathematics, and all branches of engineering, including civil engineering, mechanical engineering, chemical, metallurgy and aerospace. In all these science branches and engineering branches, we will be studying fluid mechanics in one way or another way and its related theories and applications. So, now first we will discuss what is fluid and then what are the difference between fluids and solids and how the fluid is behaving and what are the fundamental properties of fluids. So, what is a fluid? We can define a fluid as a substance capable of flowing. So, it can be gases or liquids. So, here you can see a glass of water. So, when we apply some force, some shear force especially, it will deform or it will start to flow, like you can see in this glass of water, or here you can see a bottle of water. When we apply some shear stress or some shear force, it will start to deform or it will start to flow. So, this fluid is the most vital for all forms of life. As you know, we will be using fluids as water or liquids we will be using for drinking purpose. It will be used for say all types of life activities, including bathing, taking bath, or whether drinking water or irrigation purpose or navigation purpose or recreational purpose. For all purposes, fluid, say in the liquid form of water is used, or in the form of gases, say the air which we are breathing, or all other aspects of life is required these fluids either in liquid form or gaseous form. So, as I mentioned, fluid always deforms continuously when subject to a shear stress, whether it is gas or liquid. So, fluid mechanics is mainly the study of what is happening when some force is applied on a fluid, whether it is at rest or it is in motion. So, fluid mechanics can be mainly divided into statics and dynamics. So, in statics we will be discussing what is happening, the fluids or liquids, especially in say in the condition of in static, that means it is not moving. Say for example, if we consider the water stored in a reservoir or in a tank, so it is static, it is not moving. So, that branch of fluid mechanics study is called statics. And if we consider a flowing water, say for example in a river flow is concerned, or the pipe flow is concerned, it is dynamics of fluid, or the fluid is moving, and hence the study is called dynamics. So, in all this we will be analyzing the fluid behavior based on various fundamental principles. So, the fundamental principles used in mechanics, such as conservation of mass, conservation of momentum, conservation of energy, and laws of thermodynamics, all these fundamental principles are very much used in fluid mechanics also. So, now let us see what are the major difference between fluids and solids. So, here in this figure, in this slide, you can see a fluid element. So, when we are applying shear stress, it is deforming, say an angle theta like this, it deforms, and it undergoes a strain theta due to the shear stress. And if you consider solids, a solid is concerned, say here you can see a small ball. So, here even if you apply some shear stress, it will not deform to certain level. That means until it reaches its elastic limit, it can sustain the shear stress and it will not deform. So, as you can see here in this slide, so when a shear stress is applied on a solid element, it will not deform to certain extent, and say when it reaches the elastic limit, it is starting to deform as in this figure. So, what are the major differences between say fluids including liquids and gases and solids? So, in fluids we deal with continuous streams of fluid without begin or end. So, for example, if you consider the water in this bottle, so you can see it is continuous from one end to another. So, that we have to analyze by using the continuum concept. But as far as solid is concerned, mainly we will be using say individual elements. When we are applying a force like this, a point force is applied, a point load is applied here. So, what is happening, particular say individual elements in solids. So, that is the major difference between solid and fluids. And you can see that in say in fluids, the molecules are loosely placed or loosely spaced, so that it is starting to flow by just applying some shear force. But as far as solid is concerned, the molecules are densely packed, so that the deformation takes place only after certain limit, say elastic limit. And as far as fluid is concerned, intermolecular forces are smaller than for solid. That is why the fluid is trying to flow by applying a small shear stress. But as far as the solid is concerned, there is large intermolecular cohesive forces, and hence you have to apply large shear stress or large force to make it some deformation. And as far as fluid is concerned, fluid deforms continuously when acted on by shearing forces, but solid will not deform continuously. So, these are the major differences between the solids and fluids. So, even though we are using the fundamental principles of mechanics in fluid mechanics, so these differences we have to consider in the development of all theories and when we are applying these theories, we have to take care all these differences between the solids and fluids, since we will be using most of the time the fundamental principles developed in mechanics. Now we will discuss the fundamental definitions in fluid mechanics. So here first we will discuss what is a system. So as you can see in this slide, a system is predetermined identifiable mass of fluid. Say here you can see a cylinder and there is a piston, and what is existing, the fluid or liquid or gases existing in this is the system. So say for example here if you consider a bottle of water, so the system, what is existing, the volume existing in this say 1 liter of water, or what including here in this case water and air. So this is the system. So system approach is very important fluid mechanics, since fluid is always trying to deform with respect to shear force or shear stress and trying to flow. So generally all the analysis will be for a particular system, that means a particular say volume in a piston as shown in this slide, or what is shown in this bottle of water. So that means within this space, which is predefined space, what is happening in between, that is will be generally discussing. So this is called a system approach in fluid mechanics. Then another important definition is the control volume. So a control volume, as you can see in this slide, a control volume is a finite region in space and has definite volume. So here you can see a pipe. So here between section 1 and section 2, so the fluid existing, that volume, that is the control volume, so that which we are considering. So what is happening in this is the major analysis which we will be doing. So this is the control volume approach used in fluid mechanics. So say here if you consider a pipe like this, so when the pipe flow is there, say between one section to another, what is happening, so that is the control volume approach. So now as in mechanics and all branches of science and engineering, in fluid mechanics also the fundamental quantities like length, the dimension of which is L, and unit is M, and other dimensions like mass, the dimension is M, unit is kilogram, and time, say unit is seconds, and force unit is Newton, and temperature unit is degree centigrade in the system international units. So these are the fundamental quantities used in fluid mechanics, and based upon these fundamental quantities we will be deriving the secondary dimensions, say for velocity or acceleration or force or other, say other type of quantities like viscosity and say the acceleration. All these quantities will be derived based upon the fundamental quantities of mass, length, time, and the temperature unit degree centigrade. So generally when we derive these fundamental quantities, we will be using continuum concept, since the fluid is, say as I mentioned, the flow is continuous or the molecules are very much, say we will be taking the continuum approach. So all the fluid behavior is based upon the continuum concept, and the theories are derived based upon that. And as far as coordinate system is concerned, generally in all these lectures we will be using Cartesian or cylindrical or intrinsic coordinate system, and then say as I mentioned, the other units will be derived based upon the secondary units, will be secondary dimensions will be derived based upon the primary units. And in fluid mechanics we will be using two kinds of approaches or two kinds of description. First one is called Lagrangian description. So in the Lagrangian description we describe the history of the particles exactly. That means, so we will study the path of fluid particles of fixed identity. So for example, if you consider a flow say from one section to another, we will be tracking some of the particles and then what will be happening to that particles from time to time. So that is the approach called Lagrangian approach. So In this approach, say the velocity in x, y, z direction, u can be expressed as dx by dt, v can be expressed as dy by dt, and w can be expressed as dz by dt. So, similarly, the acceleration can be expressed as x in x direction, x is equal to du by dt, or that is equal to d square x by dt square, and similarly in y and z directions. So, here in this velocity and acceleration expressions, you can see that it is mainly what is happening with respect to time, that is what we will be analyzing. So, this concept is rarely used in fluid mechanics due to the various complexities. So, here you can see the fluid is moving continuously, say one section to another section. So, to track certain particles and then what is happening with respect to time, that kind of analysis is very difficult in fluid mechanics. But this Lagrangian concept or Lagrangian description is mainly used in solid mechanics. The second kind of description is called the Eulerian description. So, here what we are doing is we will be analyzing what is happening between two sections, say at a given spatial location in the flow field, what is happening. Say for example, if you consider a fluid flow in a bottle like this, what is happening, or in a pipe flow, what will be happening, one section, it is a particular section with respect to x, y, z dimensions we will be considering, and then what is happening for various fluid particles at that particular section with respect to time. So, that the acceleration can be written as a is equal to the total derivative dv by dt. So, ax, the acceleration in x direction can be written as du by dt, or that is equal to del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So, this concept is very much used in fluid mechanics, since this has got a number of advantages, since fluid is moving continuously, say in a pipe flow or in an open channel flow. So, if you consider if a particular section and then what is happening with respect to space and time, what is happening. So, that kind of analysis is what we will be doing in this Eulerian description, and that is very much used in fluid mechanics. Now, in the beginning we have discussed, say a fluid is getting deformed with respect to shearing forces. So, shearing forces are very important in fluid mechanics. So, when a fluid is in motion, shear stresses are developed if the particles of the fluid move relative to one another. So, since fluid is moving, so you can see that, say with the layer wise there will be shearing stresses between the fluid, say if you consider a section, say between the layers there will be the shearing force or shear stress will be there. So, the adjacent particles have different velocities. So, for example, if you consider water flow in a pipe, if you consider small pipe like this, say the flow is considered say in a pipe flow. So, at the pipe wall the velocity will be 0, since say the solid, the pipe, say it is not moving. So, that the velocity will be 0 at the pipe wall, and then it will be increasing as we move towards the center of the pipe. So, here in this slide you can see that, say here in a pipe flow the water is flowing from left to right. So, here since this shearing force effect, say or the non-slip condition, so at the pipe wall here the velocity is 0 and the other end also the velocity is 0, and you can see the at the center line the velocity is maximum, and you can see there will be a parabolic profile like this as far as the pipe flow is concerned. But if you consider say in a uniform flow like this, say if there is no solid wall, or if you do not consider the effect of solid wall, then you can see as in this slide the velocity is equal in magnitude. So, that the velocity profile is like in this slide, and that is called the uniform flow. So, sometimes in open channel flow we consider this kind of uniform flow. And now we will discuss some of the important fluid properties. So, as I mentioned, mass is one of the primary quantity and which is one of the most important properties of fluid, and then another important property is called density. So, density, it is the mass per unit volume and it is expressed as kilogram per meter cube. And another important unit is called the specific weight, which is the weight per unit volume, and that is generally expressed as gamma is equal to rho into g, where rho is the density, g is the acceleration due to gravity, and its unit is Newton per meter cube. And another important property which we will be using is called specific gravity, and it is the ratio of density of fluid to the density of water. And then another property is the specific volume, it is the reciprocal of the density and its unit is meter cube per kilogram. And another important property is called the pressure. The pressure is the normal force per unit area exerted on a plane surface. So, if you consider say a plane surface like this, when you are applying normal force, the force per unit area is the pressure and its unit is Newton per meter square and expressed as Pascal. This pressure can be expressed say like absolute pressure when we are measuring with respect to certain gauge or local atmospheric pressure reference is put, then we can express as gauge pressure, absolute pressure and also vacuum pressure as differentiated in this slide. And then another important property is the bulk modulus of velocity expressed as K. It is the measure of compressibility of liquids and the unit is same as pressure. So, especially when we are dealing with the gases, so the compressibility is very important and also the compressible fluids, the compressible liquids, this bulk modulus of velocity is very important. The bulk modulus gives the change in volume of a substance as the pressure on it is changed. Generally this is expressed as with respect to solids and also with respect to liquids also we can express. And another important fluid property is the viscosity of liquids. So, this is a property of fluid by virtue of which offers resistance to shear. So, this viscosity has been observed by the famous scientist Isaac Newton, and he has observed the cohesion and rate of transfer of molecular momentum are the predominant causes of viscosity, and he has derived the Newton's law of viscosity. So, here you can see that if you consider water, so it has got one type of viscosity, and if you consider say other kinds of viscous liquids, say for example here there is some honey. So, if you just try to pour this honey on a plate like this, you can see that it is, since it is highly viscous, the movement itself is very slow and then lot of shear stress is there between the layers. So, that is the difference between say more viscous fluids and say when the viscosity is varying just like in the water and honey. So, Newton after studying all these properties, he derived the fundamental equation of Newton's law of viscosity, which can be expressed as, or he observed that the shear stress is proportional to the shear strain du by dy, and he derived the equation tau is equal to mu into du by dy, where mu is the coefficient of viscosity. So, here the shear stress is proportional to the shear strain, and then he expressed the tau is equal to mu into du by dy, or tau is equal to mu theta, where mu is the coefficient of viscosity. So, as we have already seen here, the viscosity coefficient say with respect to honey or with respect to water, the viscosity is changing and then the fluid properties also will be changing. So, Newton's observed say if the change in stress, shear stress with respect to the shear strain is linear, then that kind of fluid is called as Newtonian fluid. So, fluids for which a shear stress is directly proportional to the rate of shearing strain are designated as Newtonian fluid, and in the case fluid for which the shear stress is not linearly related to the rate of shearing strain are designated as non-Newtonian fluid. So, according to the viscosity, Newton's classified mainly the fluids into Newtonian fluid and non-Newtonian fluid. So, now in this slide you can see a fluid element like this. So, now a shear stress or shear force is applied, F is applied. So, here we are considering a fluid element of say delta x, size delta x, delta y and delta z, and a shear force is applied of F in this direction at the top and the bottom in the other direction. And now if you study with respect to the shear force, the shear strain we will be considering phi here. So, the shear force is acted on the fluid element. So, now shear stress can be written as tau is equal to shear force divided by area A, and the deformation due to shear stress is measured by the size of the angle phi known as the shear strain. So, if you consider solid, this phi is constant for a fixed shear stress, but in fluid phi increases as the shear stress is applied, means the fluid is flowing. So, since the fluid is flowing, this phi will be increasing, and this depends upon whether the variation depends upon the type of fluid. So, if the particle at a point E in the previous slide moves under the shear stress to point E and it takes time t to get there, it has moved the distance s x. So, we can express the shear strain phi is equal to x by y, and the rate of shear strain can be written as phi by t, which is equal to u by y, and the velocity of particle at t is equal to x by t is equal to u. So, that finally we can write shear stress is equal to constant multiplied by the shear strain u by y. So, here u by y is the change in velocity with y. So, that we can finally get the Newton's law of viscosity, which is expressed as tau is equal to mu into du by dy. So, this shear stress, the unit is say here m L to the power minus 1 t to the power minus 2, and the unit of coefficient of dynamic viscosity m L to the power minus 1 t to the power minus 1, and it is expressed as say in poise in system international unit. And another quantity called kinematic viscosity, when we divide the coefficient of dynamic viscosity mu by the density rho, that quantity is called kinematic viscosity, or mu is equal to kinematic viscosity mu by rho, and its unit is L square t to the power minus 1. So, for various liquids like water, air, the coefficient of dynamic viscosity varies and the shear stress also varies. So, now with respect to this variation of shearing stress and the rate of shearing strain, we can classify the fluids into various categories. So, here I will show a figure. So, this figure you can see here. So, the shear stress is plotted here on the x axis, and the rate of shearing strain is plotted on the y axis. So, in this plot, if the shear stress is varying linearly with respect to shearing strain, then we get a straight line like this, so that there is a linear variation. So, that kind of fluid is called Newtonian fluid. Say for example, water is Newtonian fluid, and if this variation is not linear, so here this line you can see the variation is not linear. So, those kind of fluid is called non-Newtonian fluid. And then if the say the strain, the rate of shearing strain starts after application of a fixed quantity of shear stress, like here say up to this point there is no deformation. So, that kind of fluid is called ideal plastic, and that is after reaching this particular point, it is the variation is linear. And then if it is the variation is again non-linear like this, then it is called a thixotropic fluid. And then again if the strain is say increasing like this in this figure, say this kind of fluid is called a dilatant fluid, and if the say the fluid is such that the shear stress, there is no shear strain, only shear stress, say if you plot like this, that kind of fluid is called ideal solids, and ideal fluid is totally say shearing with respect to, say there is a infinite quantity of say strain with respect to shear stress, that kind of fluid is called ideal fluid. So, these definitions we will be discussing further in the coming slides. So, with respect to the viscosity, we can classify the fluids as we have already seen in this figure. Now, say we will classify various liquids, say a plastic fluid. In the case of plastic fluid, say the shear stress must reach a certain minimum value before flow commences, so that we can write the shear stress tau is equal to A plus B into du by dy to the power n, where A, B and n are some constants, and a plastic fluid is said to be Bingham plastic, that means which is neither a fluid nor a solid when n is equal to n is equal to 1 in this relationship. Say for example, say toothpaste and tomato ketchup are some examples of this kind of say plastic or Bingham plastic fluid. So, here you can see when it is taking this say the toothpaste, you can see how it is behaving. So, this kind of fluid is called Bingham plastic fluid, and say in the case of, as we have seen in the previous figure, if the coefficient of viscosity is decreasing with respect to when the shear is increasing, that kind of fluid is called pseudoplastic, say for example milk. And if the mu increases as the rate of shear increases, that kind of fluid is called the dilatant fluid. So, say for example paint or the printer's ink. And in the case of fluids in which mu decreases with the time for which the shearing are applied, that kind of fluid is called a thixotropic fluid. Say for example mud gels used in drilling can be classified as thixotropic fluid. And in the case mu increases with the time for which shearing forces are applied, that kind of fluid is called rheologic fluid. And similar to Newtonian fluids, when the time variant condition, but if shear stress changes suddenly and behave as elastic, that kind of fluid is called viscoelastic. So, as we have seen in this figure, with respect to viscosity, the shear stress variation and shear strain variation if we plot, then as we have seen, say the variations, whether it is linear, non-linear, or whether it is increasing with respect to shear stress, the shear strain is increasing, or say it is decreasing. So, accordingly we can classify the fluids, and we have seen the definition of each types of fluid with the examples. Now, we will further discuss some other important fluid properties. So, as I mentioned in the beginning, temperature is of course another important property. So, with respect to temperature, the fluid properties like say viscosity may change, density may change. So, temperature is also another important fluid property, and then another important property is the surface tension. So, the surface tension is the phenomena occurs due to the unbalanced cohesive forces acting on different surfaces such as air and water. So, surface tension it occurs due to the unbalanced cohesive forces acting on the different surfaces such as air and water. So, it is generally expressed as sigma, and then its unit is Newton per meter. So, the intensity of molecular attraction per unit length along any line of the surface is the surface tension sigma indicates. So, this sigma can be expressed as dF by dl, where F is the force and L is the element length. So, due to this surface tension and other properties, there is another important properties in fluid mechanics called capillary rise. So, this capillary rise occurs, as you can see in this slide, it is due to either cohesion or due to adhesion. So, when we place a small tube, say like a small tube is placed like this, say in water. So, here it is not observed since there is no color here. So, but you can see in this slide, if the liquid is wet in type, you can see that there will be a small rise like this. So, that is called capillary rise. So, this the liquid is, you can see that both surface it is wetting. So, that is why due to the cohesion it is a rising is taking place, and that is what is called capillary rise. But in the case of non-wetting fluids, like say for example mercury. So, if you take mercury, if you put mercury in a say bottle like this and then put a small tube, then you can see that it is decrease, it is falling down. So, this takes place due to adhesion or the non-wetting type liquid, it will be going down. So, that is the capillary falling. So, there can be capillary rise or capillary fall based upon say depending upon the type of liquid due to cohesion or due to adhesion. So, this capillary rise or fall we can derive as H is equal to 2 sigma cos theta by gamma into r, where gamma is the specific weight and r is the radius of the tube which we have seen in the previous slide. And then another important property is called vapor pressure. So, the vapor pressure takes place when a liquid in a closed container, says if there is some space, small air space is there, a pressure will develop in the space as a result of vapor that is formed by escaping molecules. So, this pressure is called the vapor pressure, and then when equilibrium is reached, so that the number of molecules leaving the surface is equal to the number entering, vapor is said to be saturated pressure exerted on liquid surface. So, this vapor pressure is say especially the fluids contained in say in bottles or in say in pipes, this vapor pressure is also very important. So, these are some of the important fluid properties and definitions which we will be using in this course. So, we have seen some of the important properties of fluids, and then say some definitions also we have seen. Now, as I mentioned earlier, say due to the fluid properties like viscosity and then other important properties, say no slip condition of viscous fluid is an important properties, especially boundary condition which we will be using. So, you can see that when fluid is flowing say in a pipe like this or in an open channel flow, say the solid is say it is not moving, that means the container on which the fluid is, say this pipe or the channel where the fluid is contained. So, the solid is not moving, but only the fluid is moving. So, at the solid surface where the fluid is moving, so at the bottom, as we have seen the case of pipe flow, at the bottom and at the top or the periphery of the pipe, the velocity is 0, that since the pipe is not moving. So, the velocity the pipe material is 0, and then the velocity of the fluid at that point where there is contact between the solid and fluid. So, that velocity due to the viscous effects that will be tending to 0. So, this no slip condition occurs due to the relative velocity between the solid surface and the adjacent fluid particles is 0. So, fluid elements with the solid surface have 0 viscosity. So, here you can see in this slide, say here say when the fluid is trying to move, as you can see in this say animation, so it is trying to when it is moving, say when it is touching this solid surface, it is say there is the velocity is 0, and then say this no slip condition takes place. Now, based upon this various fundamental properties, now we will discuss the basic flow analysis techniques. So, as I mentioned, most of the fundamental principles or theories used in mechanics are also very much valid in fluid mechanics, only with certain changes. As I mentioned, the fluid is deforming or the variations with respect to solids. So, that variations we have to consider. So, some of the important analysis techniques we will discuss now. Three basic ways to approach fluid flow problems are, as I mentioned, first one is the control volume or integral analysis. So, that means what is happening in a volume, we will be considering a particular volume, and what is happening between two sections in that container or in the volume. So, that is called the control volume approach or the integral analysis. So, this approach is very much used in fluid mechanics. And then second approach is called differential analysis or infinitesimal system analysis. So, here in this analysis what we are doing is, say, with respect to say particular point, say what is the fluid properties, important fluid properties like pressure, velocity, how it is varying with respect to say x, y, z, or that means particular point is concerned. So, that kind of analysis is called differential analysis, say del u by del x, del u by del y, or del u by del z. So, like that what is happening. So, that is called a differential analysis. And the third important approach of fluid analysis is called the experimental study or the dimensional analysis. So, in the experimental study what we are doing is, we are trying to replicate the real problem in the laboratory, and then we are trying in a smaller scale, and we are trying to observe what is happening, and then we will be making with respect to dimensional analysis or various other analysis, we will be trying to solve the problem. So, that is the experimental analysis. So, these are the three important analysis techniques used in fluid mechanics. First one is the integral analysis, second one is the differential analysis, and the third one is the dimensional analysis or the experimental studies. So, in all these cases, say we have to see that the flow satisfy three basic laws of mechanics and the thermodynamic state relationship and the associated boundary conditions. The three basic laws of mechanics are the equations or the theories derived based upon the conservation of mass, conservation of momentum, conservation of energy. So, these are the three basic laws of mechanics based upon which most of the theories or the fundamental principles are derived, and then of course, we will be using the thermodynamics theories or thermodynamics equations will be also used, and then of course, the associated boundary conditions also will be used in most of the fluid mechanics analysis. Now, we will be discussing the foundations of flow analysis. So, as I mentioned, the important theories of mechanics we will be using for the flow analysis. So, 5 important foundations of flow analysis are the conservation of mass, based upon which generally in fluid mechanics we will be deriving the continuity equation, and second one is the linear momentum, or the based upon the Newton's second law we can derive the momentum equations, and then third one is the conservation of energy, or from the first law of thermodynamics we can derive the energy equations, and then we can use the state relationship between say various fluid properties like pressure, temperature and density, and lastly the appropriate boundary conditions or say at solid surface, interfaces, inlets and exits. So, based upon the boundary conditions we will be deriving the fundamental equations. In this introductory lecture now we will be discussing another important aspect, that means as I mentioned the fluid is always trying to flow or deformation takes place. So, flow visualization is very important in fluid mechanics. So, there are various techniques are used for flow visualization, just like dye or smoke or bubble discharge. So, here you can see how we can visualize flow taking place. So, here this animation shows how the flow visualization can be taking place with respect to dye or smoke, and then another animation here you can see say with respect to say here it is a gas burning. So, how it is behaving with respect to say flow visualization, how we can depict it. Or say here in this animation you can see there is a cube is placed, and then or say an obstacle is placed in a flow field, and then with respect to that how it is behaving. So here you can see the flow behave, how it is taking place. So this, say using a dye or a smoke or bubble, we can easily visualize what is happening. So that is one of the important techniques used in fluid mechanics. And then we can use surface powder or flakes or liquid flows. So here you can see that, say in this container, or if there is an open channel, if the flow is flowing, then you can use some, say flakes or some floating material, and then you can see how it is moving. So that is the way which we can observe how the fluid movement, that is either using surface powder or flakes or liquid flows. And then another technique is called floats, as we have already seen here, or neutral or density neutral floats can be used for the flow visualization. And then also we can use optical techniques like detect the density variations in the particular, say fluids, say whether density is varying from, say whether it is constant or it is varying from one to another one, say. And then another technique is called evaporate coatings or boundary surfaces, say how it is behaving. So this is also commonly used in flow visualization. And then another technique is called luminescent fluids. It is very easy to get the flow visualization by additives or bioluminescence. And then another technique is one of the modern techniques called a particle image velocity. We can, using some special equipments, we can observe the particle image velocity, and then we can visualize the flow takes place. Now, so we have seen various flow visualization techniques. So when we are doing theoretical investigations or sometimes experimental investigations, the flow patterns, we have to identify the flow patterns. So we will be using some general definitions. So we will now discuss some of the general definitions. First one is the streamline. So a streamline we can define as a line everywhere tangent to the velocity vector at a given instant. So here in this slide you can see that flow direction is this way, and then say this is the streamline. So the fluid particle, the velocity is here. So if you draw a line like this, so these are called the streamlines. So streamline as such, there are no lines, but this concept can be used for, say, to identify how the fluid flow is taking place, and then say especially in theoretical analysis we can use the streamlines for the, say, flow analysis or flow observations. And then another important definition or line is called path line. So it is actually the path traversed by a given fluid particle, say with respect to time. So here you can see initially the particle position is here, and then with respect to, say, time, say how it is traversing. So here you can see it is traversing like this. So the flow direction in this particular case is like this, but the fluid particle how it is traversing. So this path line is also used in fluid mechanics very much. And then another important line which, or the definition which we use, is called streak line. So streak line is the locus of particles that pass through a prescribed point. So here you can see in this animation, say it is the streak line is shown here. So it is the locus of particle that pass through a prescribed point. So here you can see how it is, how a streak line is defined in this animation. And then another definition is, or the another line is used in fluid mechanics called time line. It is a set of fluid that forms a line at a given instant.